back, everyone. Next up, we've got On the Fly and On the Flight, Scientific Data Analysis Beyond the Beamline by Dr. Melanie Hampel. Thank you.
Does the mic work? I think it does. Cool. Then hello, everybody. Welcome to this science track. Those of you who don't want to hear about science, now is your chance to leave the room. Everybody's saying, all good. I'm Melanie, and I'm going to present on the Fly and On the Flight, Scientific Data Analysis Beyond the Beamline. So imagine you are a scientist, and you are on a plane to a conference, and your laptop is open, and you now finally are offline and have the time to analyze your X-ray spectroscopy experiment from the Australian synchrotron. Now, some of you might ask, how often does that happen? And if you ask our Beamline scientists, it happens all the time. Now, some of you might actually ask, what is this about? Why is she talking these weird words? So what is this synchrotron thing? Why should you care about X-ray spectroscopy? Why do we do it on a plane? Who are these Beamline scientists? Why do they need to analyze the data on a plane? I won't be answering that last question, I still don't know. But I hope I can tell you a bit more about the synchrotron, about X-ray spectroscopy, about the data analysis of it, and how we use Python for it. So let's start with the big word, synchrotron. This is us. The Australian synchrotron is a research institute. We're a federal research institute under the Australian Nuclear Science and Technology Organisation. And we're here in Clayton. So just out east from here a little bit. We're all Melbourne-based, but there is a lot of our ancestor scientists are up in Sydney as well. But the synchrotron is here. And we are embedded in a rich ecosystem of other research happening right around us. So we are basically right next to Monash University, and CSIRO is up there as well. We have some other institutes around, like Moderna or nanofabrication. So lots of cool stuff happening out in Clayton. So if you dare to use the public transport and come out there, come say hi. What does it all look like? So this is our Center for Synchrotron Science. And we use the time on the open day to just fly a little drone around. And this is one of our satellite buildings, the biggest one to say. But if you turn around, you can slowly see our big science donut creeping up. This is the synchrotron. And we've recently covered it in solar cells, so we're now producing a tiny, tiny fraction of the energy that we're using. So we're here, and that's what it looks like on a drone from the outside. So now let's take the drone on the inside. So inside, we're basically this big industrial hall, lots of stuff, some server racks, lots of just concrete things around. This one that's bending right now is actually straight, but you can see that again, kind of here. And in the middle, we have these two ring-like tunnel structures, and they're at the heart of what makes our synchrotron work. So if we try to look at it from above and have a bit of a bird's eye view, that's a schematic of it. And those two rings in the middle are the heart of where we accelerate electrons. So the inner ring is what we call the booster ring, and there we take electrons and speed them up really, really fast. So almost to the speed of light, 99 point, well, very close. And once they have that speed, we then move them over into our storage ring, and there we just try for them to maintain their really high speed. Because it turns out when electrons move like that in these ring-like shapes, they give off some electromagnetic beams, so some radiation that we call synchrotron radiation. And it has a lot to do with how fast the electrons are, but that radiation for us is really, really bright X-rays. So these X-rays are emitted basically in straight lines from that ring. So we're not actually interested in the electrons that we've accelerated. We're interested in using these really, really bright X-rays. So this is what we call beamlines. So these lines of X-rays that are coming off. We have a lot of instruments in there, and we put up these what we call beamlines. So keep that word in mind. It was in the title. I hope it makes a bit more sense now. And when I talk about our beamline scientists, they're the people working on those beamlines. So they build up all the instruments, they make all those experiments possible, because at these beamlines is where experiments happen. And it's not just our scientists. In fact, our scientists are just a very small fraction of the scientists that come. Scientists come from all over Australia, New Zealand, and even more from further away. And they bring whatever they're interested in. So it covers a whole range of science. People bring really anything. And when I mean anything, we cover pretty much everything that Australia has put as a target for research. We have medical research that we facilitate. We go into agriculture, soils, plants. People bring in paintings, really cool stuff happening in cultural heritage stuff as well, because you can look underneath the layer of a painting to what old people have had underneath before they repainted their painting, and you don't even have to take the painting apart. And then you can bring it back into the NGV. So we have a lot of battery research happening as well. That's a really hot topic at the moment. So we cover anything. If I say we, that's of course the users that come to our facility and use our really bright X-rays to do their research. And those of you who like numbers, we have been operational now since 2007, so we've just had our 18th birthday party. And we have 15 of these beamlines that are operational at the moment, and we're still building 3 new ones that will be operational in the next few years. We get about 5,500 users every year, and we produce a lot of data with those experiments. So about 2 to 3 petabytes in a year, and we have to store it all on site under a lot of difficulties because we are responsible for these data for a certain amount of time as well. So that was the synchrotron stuff. The next big word, X-ray spectroscopy. And X-ray spectroscopy, in particular here, I want to talk about absorption spectroscopy. So what that means is really that we bring in a sample, we shine light on it, and the sample absorbs stuff. Okay, sample can be anything. Imagine you're that researcher, you can be a geologist, you can be a physicist, you can do medicine, pharmacy, whatever you like. You're interested in something, you bring it in. And for this type of experiment, you shine on just a single energy X-ray. So we're not doing anything fancy here. We filtered it. Just a single energy is hitting our target. As we say, our sample absorbs that. And with all that energy that the sample has now absorbed, depending on what your sample is made of, it will start emitting fluorescence light. And this light is really characteristic for your sample, and it really allows you to study the chemistry and the atomic structure of your sample. So that's the light we now want to capture. So just imagine we have a bunch of cameras there. It's a bit fancier than the one on your iPhone. It is very specific for that light that we want to capture. And not only does it look at the sample, it also tries to analyze the energy of the photons, so the light particles that come out of it. So these sensors detect those, what we then call spectra. So if you look at the distribution of how much light at each energy comes out, that's the spectra. And in this case, we have 4 of our sensors, so we have 4 spectra. So we're already dealing with a somewhat multidimensional data cube here. Now I said 4 is what we have here. That's a good assumption for 2 of our beamlines. The third one uses 18, and in a different configuration, we actually have 100. So that makes the data cube a little bit bigger. And then I told you that they actually are interested in the energy of those photons that they collect. In particular, we have more than 4,000 different energies bins that we need to sample for each of those sensors. And I haven't told you yet that this single energy of X-rays that we shoot in, we don't just do that once. We change that energy. So each time we have a different single energy coming in. And that can easily be 1,000, 5,000 to 10,000 times that we do that. And just in case I go into some jargon later, that's what we call a scan. So if we go through all of those different energies, that's a scan. And for each scan, we now get our multidimensional data cube. There's already a lot of Python involved in all of that, in orchestrating the experiment, in steering the experiment, to allow the users to even just select what they want to do. All of this is Python. But for me, the fun begins now that we don't just make the data, we also process the data. So these detectors that I mentioned before, There are sensors for the fluorescence light, but obviously there's a lot of other stuff we have to measure too. We're interested in the energy of the beam that comes in. We're interested in how much of that beam there was, intensities, times, temperatures. Lots of other data is included in that as well. So sometimes we even have to grab all these data from lots of different places to then smush them all together into one nice data cube. So you might see already that an Excel spreadsheet is not the best idea to do the data processing here. In fact, Pandas doesn't really cut it either, which is a very tabular format. So we moved to a library called xarray. And those of you who are not familiar with xarray, it's sometimes referred to as the pandas for n-dimensional arrays. So it is built on NumPy and pandas and Dask, so it has a lot of cool stuff under the hood. That makes it really easy for us to use it for computations. And there is a little example on the side where you can see that it has this idea of dimensions and coordinates, and they're named. Oh, it's amazing. You don't mix up your indices of all your multidimensional NumPy arrays, and they're having names that you can actually recognize in the code, so it makes it quite readable as well. That's just one of the many advantages of why I like xarray for this. We can have all these data variables, and they can be of different dimensionality. The energy, for example, we just measure once when the energy comes in. But then some of those things, like, for example, the times here, each sensor collects for a different time. So we have a two-dimensional problem here. The spectra are actually collected over 3 dimensions. So all of that is neatly separated in this data cube here. We can attach metadata to it, which is really important because users usually want to know when they took the experiment, what was the sample they were even looking at. And at this point, I was now thinking, it's my first time at PyQt presenting. I've never talked at a programming conference. Am I showing enough code? So this morning, I panicked on the train and made a new slide with more code. Then, just before the talk, I took it out again. Now I moved it to the end. So if you want to see how we actually do some of the processing here, I have an example slide at the end, and maybe we have some time for that later, so stay till the end. For now, I can just show you that we do have a lot of those functions and processing customizations on all the things we want to do with our data set. So we might want to calibrate things, we have to correct for things in the detector, in the electronics, normalize, calculate a bunch of new stuff. So our data set now, after we apply some of those functions in some sort of pipeline-y way, we now have 28 data variables. So I didn't bother printing them all out again. And if you can't read this, totally fine. Just believe me, we calculated a bunch of stuff. So that's cool for the users, except they don't want to see a bunch of stuff. They just want a line at the end. So out of all of that, we then extract something that we can give to them again as a table. Human readable, not these weird formats that we initially had. Remember, they might have been in a lot of different places as well. They all have different data types. So here, we bunched it all together, calculated things, and now put them into something human readable. And actually, it's really important that it's human readable and accessible straight away. So if you are a scientist coming to the synchrotron, you don't have infinite time. You can't just show up and be like, hey, I would like to use your X-rays. It's a process that only grants you very limited time, and that's what we call beam time. So that's the time you're on site. It's basically night shifts as well. It just runs. You have to use the time as best as you can. You have to make decisions on the fly because you only have this one chance. If you're back home and 2 or 3 weeks later find out that you've been looking at the wrong sample, that's too bad. You can't come back that quickly. You might want to check whether the thing you're looking at, if these things are even in your sample before you start a 6-hour scan. Is it even visible? Is it measurable? So it's important that after each of these scans, and remember, scan was one experiment, one sample. Sometimes we scan the same sample 2 or 3 times. After each of these scans, the scientist wants feedback pretty much straight away on has it worked. They can't go into the whole science and do it all in a fly, but it's important for them to check has it worked. So we produce all these data outputs immediately. The moment the scan is finished, the pipeline gets triggered. We produce this, we call them XDI file, but it's basically a text file. So that's really cool. The scientists can now look at it. They can quickly import it into their domain-specific software that they need to analyze. Because keep in mind, you might be a biologist, you might be a geologist. The analysis of your data will be completely different. And they can make adjustments now while they're still at the beamline, while they can still see, oh crap, I damaged this sample, ooh, I need to dilute this a bit more so I can see this effect. All of that has to happen immediately. But on the flip side, if we automatically produce data sets at the end, we have to make a lot of assumptions for the processing. Depending on the sample, maybe our parameters are not the right one. You can maybe say that your data are okay, you can keep collecting, but to actually gain insight into what science you're doing, you might want to reprocess stuff. You want to choose your parameters a bit, you want to tweak them a bit, you want to look at different things in your data set. And this is where it really depends on what type of user you are. And we get the whole range. So we have some that like a bit more hand-holding when it comes to code, and we have others that really like diving into their data straight away. So for that, we have developed a suite that has different approaches and provides each type of researcher, in that sense, a way to interact with their data. So let's start with those that are a bit more coding-affine, and they can reproduce those pipelines. So all these different steps that we automatically perform, they can perform them in a Jupyter notebook. So here's, for example, a Jupyter hub that we give to our users. It's accessible there. They can dive straight in and really tweak as much as they like. They have all the control. It's customizable. It's reproducible, which is for science also really important, that you keep track of the parameters you're using. All of that gets written in the metadata as well. And depending on what your domain is, you can even integrate these pipelines into your further processing flow. Now, not everybody of our users is comfortable doing that. We provide some command line interfaces as well for those that are comfortable with command line interfaces. A lot of people find them very scary. But basically, these pipelines, all these steps that we automatically do, they're accessible via a simple command. But there is a bit of configuration. We have some config files, some YAML files, basically, where you can tweak a few parameters, and you can reprocess a whole bunch of samples again. You can scan your whole folder of experiments to get an overview over when have I changed sample, when did the temperature drop, when did I change whatever else. So we use Typer for that, and a lot of times that's used also for file conversion. So sometimes our users want to interact with the raw data and are just really scared of the weird data formats that the detector spits out. So we can just take this xarray, dump it into an HDF5 file, all the data is there, they can take it home and do whatever they like. Now, as I said, command line interfaces can be scary for a lot of people. Jupyter notebooks can be scary for a lot of people. So a lot of our users like buttons. So we made GUIs. We used PyQt for this, and that's really our most approachable way to interact with the data, and it makes the visualization really fun. PyQt Graph has some interactivity in there that we've used, and they can really, on a slider, refine their parameters and see immediately what it looks like. How does your final data product change? How does it enhance certain features or not? All of that is visible here. So this is some of the spectra that I've mentioned before. So when I said these fluorescence spectra that these weird cameras were capturing, that's what you see in that top panel. And I haven't told you yet that the users aren't usually interested in the whole spectrum, but just in slight portions of it. And how you select that portion really impacts what type of science you can see. So you select that portion, you can refine the portion, and that is just as a single energy. And remember, we did this like 1,000 or 4,000 times. In this time here, it's 717 times, so it was just a little sample here. But if you want to look at it over all those different incoming energies, that's what we then see at the bottom. So let's see if I can give a little video here. Yep. So you can easily refine and reselect if you want to look at a different element, a different chemistry, so to say. You can just refine things there. You can recalculate your final spectra again. There is the way to even just inspect your spectra as you go through increasing higher and higher energies of the beam that you shoot at your sample. You will see different features in your spectra. And all of this is now accessible to users who are really scared of opening their data files. So how do we give that to users? How do we make it available for them? Well, there are a few different ways. First of all, while you're at the beamline, in the little hutch, they are computers. These computers is stuff we control, so we can put programs on them, and they can use them. Obviously, all the data are nicely mounted on there as well, so the users can straight away use these tools to inspect their data. Now, at some point, they'll have to leave our facilities. I know some really want to stay forever, but they have to leave and now have to do this from their home institute. We have a desktop computing infrastructure platform. We call it ASCII. And it basically gives the users a desktop environment on our systems. It has a bit of smarts built in, so the users have to log in, and that already knows what were your data. Where do you have access to other experiments? All of those data get mounted immediately, so again, they have it really easy to use that. It is a desktop interface, so they can look at things. They don't have to write scripts, they can click things, they're happy with that. But under the hood, it really is just a Python package. So to our Beamline scientists who really want to delve in, we just give the Python package. It has its own virtual environment, you can just run it, and the beauty of that is it works on the plane. So we made them all happy. Or to leave it with this little meme, we now have Python on the plane. So thank you. How are we going for time?
So firstly, you two get a speaker mic.
Thank you.
There's a sticker in there as well for you. So
oh, perfect.
We'll have time for questions. So
do we want questions, or would you like to see a basic example I mashed up on the train this morning? Both. Question first.
Okay, so we've got the microphone flying around somewhere. Yep, so just stick your hand up and get to.
Thanks, that was an awesome talk. I was just curious, do you serialize everything as NetCDF, or do you use ZAR or other formats?
As a what? As a?
So do you also serialize to say like ZAR or something else, or do you exclusively use NetCDF?
No. NetCDF is the choice, so to say, because a lot of our detectors can spit that out, and xarray is inherently built on that data format. HDF files is really the only other thing that we give to our users, apart from ASCII format text.
Thanks.
Howdy, thanks for the talk. In terms of designing the user interface that you have there, the bespoke one, were there any considerations for the fact that you had like a technical audience who are looking at it, but people who are not familiar with the actual framework and libraries in Python? Like, how do you design an interface around that?
Well, if it comes to the actual user interface, our front-end designer is at the back there, and he made some really beautiful interfaces. Programming-wise, it's just in this library. So if you really want to delve in and use our stack, you need to know xarray pretty well. So it gets quite specific if you really want to delve in, but you always have the chance to take this object, take it home, and put it into your own code. So we're not the only facility doing this. There are a lot of research teams who have other approaches to do, for example, detector corrections. So we provide them with all those data as well. But if you really want to do something in a different domain, you have to import it in there.
So in 1978, Anatoly Bergolsky was hit in the head by a high-energy proton beam at a synchrotron. I guess he survived. Has anyone been hit by a beam?
I've not tried this. We have some doors, if you open them, alerts go off, the beam dumps immediately. We try to be very secure on that. I have no idea. A proton beam is a bit different as well to the electron beam. I know that we have actually some experiments on radiation therapy, and I think it's dogs that we use, but we don't just hit them in the head with proton beams. So there is, there's other applications, but no, I can't comment on that.
How are you wrapping your GUI for the non-technical users? Are you using something like what are you using?
PyQt. So it just has a entry point, and we can call it. We actually use UV to have the whole suite built together. So from there, you can just use the entry point into PyQt.
Do you use something like the UV script interface? So it's
Yep.
just a one-click? Yep. Interesting.
It's those.
Yeah, amazing talk. Like, how do you guys manage storage? Because my understanding, I have like 3 petabytes per year.
Yeah, that's a good question. How do we? Obviously, those data files have been getting larger and larger, and as we've been building new beamlines with more detectors and better resolution, yeah. I think we have about 10 to 12 petabyte on site, and we are in the process of cleaning them up because you can't just keep going. There are regulations on government-funded research. We have to keep the data for a certain amount of time, but at some point we have to give the responsibility to the universities to, hey, these are the data you guys wanted for your research, go and do something with it. But we keep them actually for quite a long time, and yeah, we're reaching our 12 petabyte limit now.
So I guess storing in cloud storage is a no-go. Like,
It's all on site.
okay, thank you.
I think we've got one more question, then we'll go for the demo. Very
Yeah.
quickly.
Just a continuation of the data storage question. Do you compress the data that you have from observations lossily at the time? And is there any research into potentially having maybe lossy compression that still retains sufficient science, or do you just keep the file as they are?
I think every beamline does their data compression or even the data file formats completely differently. So it's very specific to the type of data you're dealing with as well. We have some beamlines that barely produce anything. You can fit it all on, I don't know, a floppy disk. But other beamlines have really large data sets. So it's very, it really depends. And I'm not the right person to give you the, detailed insight there. Sorry.
Would you like to finish up by showing us that code slide? I think we have about 3 minutes.
Yes, I made a very, very simple example here. So with xarray, one of the things I found out very early was you don't want to inherit from an xarray object when you build a class. It's very fragile. You might be returning the wrong objects. So xarray has this cool thing they call accessors, and the class looks a bit like this. So you initialize it only with the data set that you have, and that's really it. But then you can deal with it like a normal class. You can refer back to your objects, and here I made a property that in this case is just an example of pulling out a key from your metadata and giving you that back. And then you can also have methods. So we have a really cool correction method here, and it takes an integer parameter. And what it does here, so those of you who know pandas a bit might find the syntax really similar. We take our energy column, well, in xarray land it's called a data variable, but it's the equivalent of a column in pandas, and we just multiply it, because under the hood it's all NumPy, so you can just throw it all together and it handles these things really smartly. And we've now made a new data variable called new energy. And just to show you that something's happening, we're also having a really important processing step print out so that you get the info straight away. As I mentioned in one of the questions, netcdf is really the data format underneath. So dumping into netcdfs is really easy, and loading netcdfs is really easy too. So we just have an example data file here that we load in, and then we can check whether the new energy is part of our data set, and it's not. We can now apply our accessor, so we can access it if it was a method on our object. So we called it XRF, which means X-ray fluorescence in the field. And now our XRF accessor can be accessed as if it was an attribute or a method of this data set. And we can look for our correction property, which gives us the correction info. And we can also call our really cool correction method with that parameter. And it showed us that we have done a really important processing step now. And now if we look if new energy is in our data set, it's there. And I could have printed it out for you, but it's just a bunch of numbers, and you have to believe me that it's 5 times larger than the original energy.
Thank you, that was really great. One last round of applause, and then we